Hey everybody, welcome to this class 15B, where we will continue to look at mathematical tools that are quite useful in thermodynamics. And in this class, we will be looking at path and state functions, at exact and inexact differentials, and at path integrals. Now, the concepts that we will be discussing today build on the contents of the previous class, 15A, and these included partial derivatives, the concept of the total differential as a mathematical tool to describe changes in thermodynamic properties, which are furthermore governed by the equation of state, of course. And we also looked at a few examples. We applied the total differential to the ideal gas law, which is a relatively straightforward example. And what was also nicely shown was that you can actually use the total differential to prove mathematically that entropy increases when the internal energy increases, and that entropy also increases when you increase the volume. We had made these observations before, but that was more on a semi-empirical basis, and in this case we use this total differential to prove it mathematically. In the previous class, we had also seen that partial derivatives and total differentials are useful to describe changes in a thermodynamic system if those changes are relatively small. And what I mean by that is the following. Let's assume we have a function, z, which is a function of independent variables x and y. And let's assume that the variable x changes from some initial value to a final state value, which is equal to delta x, and the same thing for y. You have delta y being equal to the final value of y minus the initial value of y. Now, if delta x and delta y are sufficiently small, then we can take the expression for the total derivative and then replace sort of the dz with the delta z, and the dx with the delta x, and the dy with the delta y to find the change in z because of the change delta x and delta y. Remember that this is kind of a condensed notation. What this doesn't say explicitly is that these partial derivatives, for example, are evaluated at a certain point, which we could call x naught and y naught. And these partial derivatives are in general valid only at or very near this particular point in the plane. But now you may wonder, so how are small changes, or terms like very near, how are they actually defined? How can you tell whether something is small? Well, what we mean by that is that changes delta x or delta y, which lead to a change in delta z, they are considered small if this delta z divided by its nominal value, z naught, which is what you get when you plug in these numbers. If that's much smaller than 1, then you're talking about relatively small changes. Well, you may immediately wonder, what if delta x and delta y are not small at all? Obviously, you cannot use this replacement anymore. You have to do something else. And the thing you have to do is to compute an integral. Your delta z formally is defined as an integral over the total differential dz, where you start from an initial point x and an initial point y, and you integrate to a final point x and a final point y. And using this same expression again, you see that this integral here can be decomposed into two terms, one integral in x and one integral in y. Now, if you look at this integral here, you may notice that what we are doing takes us along a path in the two-dimensional plane, the xy plane. That xy plane is shown here, and we have a point that's given by the coordinates xi and yi, and then there's a certain path that takes us to our final destination, a point with coordinates xf and yf. And because of this path that we follow in the two-dimensional plane, this type of integral is also called a path integral or line integral. I can also think of a second path that takes me back to my point of origin, and in this case it's obviously a closed loop. And for these kind of line integrals, people have come up with a separate symbol, which is this integral with the circle in it. Now, earlier on in this thermodynamics course, we came across what we call state functions as well as path functions, and we will go more deeply into their definitions later on again. What's important to know is that state functions and path functions, when you integrate them using these kind of path integrals, they behave quite differently. And we will see an example of that, and we will see an example of how to evaluate such an integral in the following movie by Wout.
Ladies and gentlemen, welcome to a new video about thermodynamics. This video is going to be about state and path functions. And over here it will be explained what the difference is between a state function and a path function. And in the PowerPoints we will continue in explaining the applications of state and path functions in thermodynamics. Okay. Over here we have another mountain, and on this mountain there are two male rabbits, rabbit 2 and rabbit 1, and they both want to get to a very pretty female rabbit over there, and there are actually two paths which they can choose, and rabbit 2 chooses to use path 2, and path 2 looks like this. Rabbit 1, however, chooses the other path. And of course, if you want to run for a nice female rabbit, then you need to have then of course when you get there you want to have as much of energy as possible. So both our rabbits are very interested in the amount of work they need to apply in getting there, and they're very interested in their increase of potential energy. And of course it was asked to us to calculate this. So that's what we're going to do. And as we know from definition, we can calculate work by using the integral of the force using the inproduct with the path ds. And by computing this inproduct, it will leave me to fx dx plus fy dy. So for both rabbits I know that the force in x direction will be mg over 4, so the gravity force over 4 multiplied by y, and the forces in y direction will be equal to gravity, mg. And both paths have a mathematical description. Path 1 is y2 is the square root of 5x, and this is the description for path 2. So of path 1, so this path 1, path 2. And now we have to do the mathematics. And it's most convenient to have everything in one single variable, so I'm going to express the dy as a function of x, and that will look like, and you can check for yourself whether this whether you get to the same answer. dy2 is equal to the square root of 5 over 2 times x to the power 1/2 minus 1/2. So that's the dy2, and dy1 is equal to 1 over 20 x dx, and I think I forgot the x here, dx. Okay, so these are my descriptions for the paths of rapid 1 and rapid 2, rapid 1, rapid 2. So let's first calculate the amount of work rapid 1 needs to apply during his walk to his lady rabbit. And for this I have to substitute these values, so I'm going to do this. It's mg over 4 times y is over there, so mg over 4 times the, and we're looking at rapid 1, so this one, 1 over 20, 1 over 40 x squared, apologize me, 1 over 40 x squared dx, plus, and I will substitute dy, mg, and dy1 is 1 over 20 x squared dx. So I can get rid of this one and write everything between brackets. So I eliminated all terms having a y. Now, and since the x coordinate is from 0 to 20, I have to do my integration from 0 to 20. And now I can solve this. So I will show some steps of solving, not all steps, so you can practice for yourself. You can do this assignment for yourself. So please stop the video and try to work it out by yourself. And it will lead to mg divided by 160 multiplied by 1 over 3 x to the power 3 plus mg over 40 this one shouldn't be there, no, it shouldn't be there, x to the power 2 between 0 and 20, and this will lead to 16 times 2 over 3 multiply by mg plus 10 mg. So the final answer will be 26 2 over 3 mg. So rapid 1. Let's continue for rapid 2. So I know the work the rapid 1 has to apply to get over there. So rapid 2. Well, I have to substitute the values again. So for rapid 2, fx is mg over 4 times y. Y is square root of 5x plus fy, and fy is mg, and the dy of the second rabbit is square root over 5 divided by 2 x to the power 1 to the power minus a half dx. Put it between brackets. So, and now I can do my integration again. And again, I have to do my integration between 0 and 20. So, if I work this out, and again, please try it for yourself first, I will find mg over 4 times 2 over 3 x to the power 3 over 2 plus mg multiplied by the square root of 5 multiplied by the square root of x from 0 till 20. And from this I can get to my final answer, which will be 33 1/3 times mg plus 10 mg, which will result in 34 1/3 mg. So we can see that the amount of work rabbit 1 needs to apply is 26 2/3 mg times the gravity force, but rabbit 2, oh, this is a 1, but it should read a 2. Rabbit 2 needs to apply 43 times the force of gravity amount of energy. So it will this rabbit 2 will be much more tired when he gets to his lady rabbit. It's better to take the route of rabbit 1. But now let's look at the potential energy each rabbit has. And the potential energy can of course be calculated using, and I'm going to make a little section over here. The potential energy can be calculated by taking the integral over mg delta y. So these two m and g are constants in our case. I don't think that the rabbit will lose a lot of weight. And dy is the increase in height. So let's calculate this. EP, potential energy of rabbit 1, is the mass of the rabbit times the gravity of the rabbit multiplied by dy1. And I can again substitute these values. 1 over 20 x dx. And it goes from 0 to 20 again. 0 to 20. This will lead to mg 1 over 40 x squared from 0 till 20, and this will lead to mg times 400 divided by 40 is 10 mg. So that's the amount of potential energy rabbit 1 has gained during the travel up. So let's look at rabbit 2. So the potential energy of rabbit 2 is again the integral over mg dy is equal to the integral of mg square root of 5 over 2 x to the power minus 1/2 dx. And so we can integrate between 0 and 20 again. That is equal to, I'm going to write the answer down, but again feel welcome to do it yourself. This will be equal to mg, so continue, mg square root of 5 x to the power 1/2 between 0 and 20. And if you calculate this, it will lead to mg10. So rabbit 2 has gained 10 mg of potential energy as well. So these are the same, these values, but these for the work are different. And this is actually the difference between a state function and a path function. So over here we have a state function. And a state function is a function which is only dependent on the current state. So state A, location A, and state B, location B. And it doesn't matter what happens in between. Whereas the work is a path function. Path function. And a path function, like you can see, depends, so the outcome depends on chosen path and initial and final state. And actually this is very convenient in thermodynamics. And Jeroen will tell us in his slides why this is really convenient. Enjoy the slides, and I hope this helped you gain a little insight in state and path functions. Good luck with the lecture.
Okay, so in Wout's movie we saw a nice example of how to work out integrals like this, these path integrals, and we also saw that it was helpful to write this particular path in a form y of x, and then compute the differential dy such that you end up with an expression that's actually the differential in dx, and that makes life easier because you could combine everything into the same integral over the variable x. We also saw the different behavior that I was referring to earlier on. What I mean by that is that path functions, if you take the path integral of a path function, then the value of the integral is actually dependent on which path you followed, as opposed to state functions, where the path integral gives a value that's independent of the path followed. All right, that was formulated nicely in words, but how to distinguish between path and state functions mathematically? Well, for state functions, we can write a total differential, which is also called an exact differential, which we will denote by just a straight d, like the d of the variable or state function z. Whereas path functions, they have what we call an inexact differential or non-total differential, which is something that depends on the path when you integrate it. And to make this distinction, we denote this with this Greek delta, delta z. We've also seen that the integral, the path integral of a state function, which is described by this total differential, has a value that does not depend on the integration path. And from this, you can show quite easily that if you follow a closed path, the integral should be 0. Again, as opposed to path functions that are characterized by a inexact or non-total differential, if you integrate those, then you will find a value that does actually depend on the path of integration. And in fact, if you do a line integral along a closed path, this integral will yield a value that's non-zero in general. By now, we've come across quite a zoo of different d's: a straight d, a Greek delta, a curly d, a capital Greek delta. So let's try to get an overview of what these are exactly. And for that, let's assume that x is a path function and y is now a state function. Then if we want to write down the differential for x, well, that's a path function. And in that case, we would like to write this Greek delta because it's an inexact differential. Whereas for y, we'd like to write a straight d or dy because this is a state function for which you can write a total differential. Then we've seen in the previous class this curly D, which refers to partial differential changes, which are the changes that you will get when only one of the independent variables is varied, while the other independent variables are held fixed. So you would write, for example, curly dy. And then there is the capital Greek delta, which indicates a difference between two states. For example, the difference between a state before and after a certain thermodynamic process. So we have a final state value and an initial state value, and their difference is delta y. Now remember that such differences that you express by this delta, they do not apply to path variables. For example, if you're talking about work that has to be done to take the thermodynamic state from one value to another, then it's simply the work that is needed. There's no such thing as a difference in work, or the difference between the initial work and the final work. All these things are meaningless. We have discussed that during class 2, and it's written here in fine print, so you better take notice of the fine print. Now, let's consider also that we are going to integrate this path function x and the state function y. We're going to integrate them from a state 1 to a state 2. Then we can write for the path function, well, we write the integral, it's this path integral again, for this inexact differential. And that gives us our value x. And again, like we just discussed here in the fine print, this is not denoted as delta x because, well, things like delta W or delta Q, delta heat, are meaningless. By contrast, if we have a state function, which is characterized by this total differential, in that case, the path integral will lead to something that we can write as a difference, delta y. Note also that these d's, dy, curly dy, and delta y are infinitesimal changes that still have to be integrated, whereas capital delta y is a finite change that has been obtained after integration. Now, I think this slide speaks for itself. You might want to take a few minute break before you continue. See you in a minute. Now, before we start looking at some actual examples from thermodynamics with these state functions and path functions, I'd like to go back to a little bit of math, partial derivatives. I will go through this rather briefly because I think you can all look this up for yourself very well, and you have to look at chapter 5 of the Watt Reader. And what you can learn there is about 3 special relations that are useful in thermodynamics. One is the reciprocity relation, which basically says that if you have a partial derivative dx dz, that's the same as dz dx, or 1 over dz dx. So you can treat this as a normal ratio. In here, well, if you want, you can stop the video and have a short look where this is demonstrated with the help of some complex looking function. There's also another relation which is called the cyclic relation, or the -1 rule, which says that if you have a partial derivative dx dy, if you multiply that with dy dz and multiply that with dz dx, then you end up with something that's -1. And note also these variables that are being held constant here. And then there's the chain rule, which is the kind of stuff I always really like because it allows you to introduce a whole new variable in the equation. For example, if you have a partial derivative dx dz for a fixed value of y, we can write that as dx dw times dw dz. And that is kind of similar to this reciprocity relation here, right? This is like working with normal ratios of numbers. And from this step, you can also prove this one with the help of the reciprocity relation. There's also another property of partial derivatives that is worth mentioning. It's also a property of the total differential. So again, we have a function z of x and y. And look at this redefinition here. The partial derivatives are actually rewritten as m and n, which by themselves are also functions of x and y. And what you can do now is take again a partial derivative, but this time to the other variable. So this one was first differentiated with respect to x, and now it's differentiated with respect to y, and that gives you this mixed differential, or a mixed partial derivative, I should say. And the same goes for this derivative of n. Now, you notice that the ordering of dy and dx is different for these two. But if you have an exact differential, like this total differential here, then there is a theorem by Clairaut or Schwarz, it comes by different names, that says that for exact differentials or for state functions, the ordering doesn't matter. And these two derivatives are the same. This is actually one way of identifying a state function. So, well, this is basically what I've just said. So this is not valid for a path function. So again, a little bit of repetition, as well as also a bit more of a connection with thermodynamics. We've seen that state functions, which are also called point function or state or point quantity or state point variable, they only depend on the state of the system, and they don't depend on the path that led to the particular state. What's also important to realize is that a state function always describes an equilibrium state of the system. And examples are things like temperature, pressure, internal energy, entropy. And this contrasts path functions, which are also called process function or path process quantity or path process variable, which describe transitions between equilibrium states as shown in this diagram here. This is a PV diagram. You have one state function here in 1, and there's another state function characterized by P2 and V2. And a thermodynamic process is a transition from one state to the other. And the process is described by a path function. For example, work or heat or entropy generation, which is the additional entropy that's generated because of irreversibility. Now let's take a look at a concrete example from thermodynamics, and let's take a look at the Otto cycle. Now the Otto cycle we will discuss in more detail in class 18, but just like many of the other cycles that we have seen, it combines 4 states and 4 processes that form a closed cycle, as shown here in these diagrams below. And what it basically is, well, it's the cycle that describes most combustion engines. So you have a piston cylinder where the crankshaft rotates and first compresses a gas mixture that's inside. So the volume is decreased, pressure builds up, and the work that's done can be calculated by evaluating this integral, this path integral. Now this is a inexact differential. It's a path function, and the result of the integral is shown here in green. Now When the whole thing is, when the gas is compressed, then the spark plug ignites the gas mixture, and very suddenly, without this volume really changing, the pressure builds up. And then afterwards, because of the high pressure, the piston will be pushed down again, and this will allow the volume to expand and the pressure to go down. And during this particular process, work is done on the crankshaft. So whereas previously the crankshaft had to do work to compress the gas, now the gas is giving back work, and the integral that corresponds to that is a surface that's actually bigger. Now the interesting thing is what we see when we follow the cycle. When we start from point one, then if we compute the entire integral, the path integral along this loop, then we find a value that's non-zero. That's the net work that's done by the piston cylinder during one cycle. And now you see that's actually important that path functions don't produce a zero integral value, because it's because of this non-zero value that we can actually obtain work from an engine. Okay, this kind of concludes this class. What you see here are the important formulas that you may try to memorize every once in a while. And of course, we would also like to give a lot of credit for to Genie Stoffels for letting us use and edit her slides. And like the previous time, it may be a good time to activate your long-term memory again by the help of these two questions. Um, just try to decide for yourself what was the purpose of this class, the main theme, and which were the three most striking elements or eye openers in this class. All right, that was that, and see you online. Bye.